Hello, everyone, and welcome to this course on time-varying functional connectivity and to this talk on null models for characterizing brain functional dynamics. So in the first talk, Julia Preti presented different models for describing these dynamics. Here in the second talk, we will discuss null models and how null models can be used to describe and better characterize the nature of these functional dynamics. This is work that was presented in that paper that we published last year in collaboration with Thomas Yeo from the National University of Singapore and Dimitri van der Veel from EPFL. So if you want to know more details, it's all in that paper. Before going to the methods, methodological core, I would say, of the presentation, let's start with a few motivational examples. And I wanted to start with this result presented in Zaleski and collaborators 2014. I'm sure most of you know that result, where they apply a sliding window correlation approach, so very simple, very basic approach on fMRI time series, and they observe what you see here on the left, which is large fluctuations of this correlation coefficient, and importantly, coherent across all pairs of brain regions fluctuations of this correlation coefficient. And when they compare it to a null, they see that the average fluctuations in null data is almost flat. And they conclude, they say that these fluctuations therefore are significant. Okay, so this is a first result. Let's now compare this to something that we found and show in our 2017 paper, which is another paper than the one that I just showed in the previous slide, where we use the same approach, so sliding window correlation applied on the HCP dataset. We also find these large fluctuations represented by the red curve. But in our case, when we compare it to null data, it's less obvious and less easy to make the distinction between the two. So we see that also in null data, we have these large fluctuations of the correlation coefficient. Okay, so what does that mean? Does it mean that someone is right, someone is wrong? Does it mean that someone used the wrong method? What can we conclude from this? And the apparent contradiction between these two results was the starting point of our paper on the interpretation of null models. Another example using a popular paper and result in the dynamic functional connectivity literature is this work by Diego Vidore and collaborators, where they describe the transitions between different states, connectivity states, at rest and during tasks. So they show that these states are organized into two different metastates, and when they compare these to the null, this is what they find. So they show that actually, depending on the null that you consider, you will reproduce or not this organization into two metastates. So here, the second null is the subject level multivariate autoregressive one that reproduces this metastate. Okay, so that might be a lot of information. And the question at this point is, how do we interpret this? And what conclusion can we derive from this about the nature of the dynamics in the original time series? Hopefully, by the end of this presentation, you will have the methodological tools to answer these questions. Okay, let's now jump into the core part of the presentation. So I will first have a very quick 101 crash course on null model testing. Then I will present popular null models for fMRI time series, because fMRI time series have some statistical properties that need to be accounted for when defining a null model. And then I will discuss interpretation that we can have of these results. Okay. Let me just keep track of the time. Null model testing 101. So what is a null model useful for? What is a null model useful for? When we are facing some data, such as this time course, we might have this question about the statistical nature of this data. For example, is it Gaussian, is it linear, and things like that. So the way to approach and answer this question is using null models. So how does it work? Well, we will denote this original data. That's not very surprising. And then we will define a model M that we want to test in order to see whether this model could be a good candidate to represent the original data. So how do we do that? Well, we identify the model parameters from the original data, then we generate a lot of what is called surrogate data using these model parameters M. And then we define one metric M that we compute in the original and surrogate data. So we will have one original measure and a distribution of surrogate measures. And then we compare the measure in original data and in surrogate data. If they are different, then it means that M is not sufficient to fully describe the original data. That doesn't mean that M is useless or that it is bad, but there is a sign that something in the original data is not captured by the original model. If M0 cannot be distinguished from the distribution of surrogate values, then there is no evidence that M is insufficient. So that's a bit frustrating because we would like to conclude that M is the model representing the original data, but the only thing that we can say here is that there is no evidence that M is insufficient. So a priori, if M, small m, is the measure or the quantity of interest from the original data, then it's a good sign that the model M is a good candidate to represent our original data. So this was to sketch the theoretical framework. Let's now get a bit more concrete and introduce the simplest null that exists, I think, which is the univariate Gaussian null. So what is a univariate Gaussian null? That's essentially assuming that here each time point where t index is time, so the horizontal axis here, each time point follows a Gaussian distribution with a mean mu and a standard deviation sigma. Quite simple, I think. Here I have also one line for operation on data. You will see later on why this line is used for, but here we don't use that line. So from this model, as I said, once you identify it from the data, so you identify the parameters mu and sigma, then you can generate as many surrogate time series as you want, where each time point here will follow a distribution of mean mu and standard deviation sigma. What are the data properties that this model preserves? Well, the mean and the standard deviation, I think that's quite obvious. And the important thing here is that if you want to compare original and surrogate, you need to use a metric M that is not defined by mu or sigma. Otherwise, by construction, you will have an equivalent value between MO in the original data and M surrogate. Okay. So you could, for example, compare counts of threshold crossing. So you define a line here and you count the number of times the curve here crosses the line, and you compare it to the same metric evaluated from the surrogate data. That's one valid metric. You could compare kurtosis. Kurtosis is a measure of non-Gaussianity, and since your null is that the data is Gaussian, having a metric of non-Gaussianity is also a valid metric to be compared between original and surrogate data. And you could essentially define an infinite number of different metrics that could be compared between original and surrogate data, but again, nothing involving mu or sigma. How do you conclude when you have these values MO and MS? if MO is different from MS, then it means that the data, the original data, the green data here, cannot be fully explained by a univariate Gaussian distribution. For example, because there is autocorrelation in the time series. That's typically what you will observe in fMRI time series. Okay. If, on the contrary, MO is equal to MS, then there is no evidence that the data cannot be explained by a Gaussian. And that's the only conclusion that we can draw from this. Okay, so I think this is a simple null model. We will see a bit later that there are more complex null models that are more relevant for fMRI applications and dynamic functional connectivity in particular. But already at this point, I think it's important to highlight the fact that the results require careful interpretation. So if you reject a null, that doesn't mean that the model is useless. And that's an important point that I want to make, because I see quite often in some papers that people want to reject the null in order for their findings to be significant or to reflect something that is neurologically relevant. That's not the case, right? What we are doing here is to see whether a model is good at describing data. If it's not good at describing data, that just means that it's not capturing all the information in the data. But that doesn't mean that it's useless at all. And to illustrate this, I want to show you this example that reports the distribution of hate in US women. So that's the distribution. And if you identify and try to test whether a univariate Gaussian distribution would be a good fit to this, well, you would compute a Gaussian distribution here with a mean of 64 inches. That's the average height of women, US women, and a standard deviation of 2.7 inches. Thus, then, if you use a test statistic, small m, that is the number of individuals taller than 75 inches, then you would find that MO is different from MS, because with this null model, it's almost impossible to get individuals that are taller than that. Yet, in reality, you find people that are taller than 75 inches. And so that means that M0 would be different from MS. So in terms of null models, I just wanted to take this example to show that rejecting the null doesn't mean that the model is useless. And in this case, I think we would all agree on the fact that a Gaussian representation of this distribution is quite useful, right? It's informative to know that the average is 64, the standard deviation is 2.7. And okay, it doesn't capture the tails and the extreme values that you have there, but it's doing a good job in describing the first order information, I would say. So framing it differently, it's a bit like reframing this question in terms of system identification and on whether you are happy with what the model is describing about your data. So if you are interested in extreme values or very tall or very small people, then the model is not going to be good. If you are interested in, I don't know, defining different sizes for clothes, then this distribution might be good. Okay, let's now move to the second part of the theoretical presentation, which is on null models that are adequate for fMRI time series. What is the difference between a typical fMRI time series dataset and the previous case? Well, the main difference is that fMRI time series are multivariate, and that's a crucial thing that needs to be accounted for when defining null models in our applications. So we'll have to define multivariate models, but also multivariate statistics to test between original and surrogate data. Okay, first one I want to consider and to show here is also the simplest one, just the multivariate extension of the example I showed before, where we have multivariate time series again, so the mean is 0 here. The model M now would be that each time point here separately follows a Gaussian distribution with mean 0 and covariance or correlation matrix sigma. Okay, again, here there is no operation that is performed on the data. we can play the same little game and generate surrogate time series that are for each realization multivariate again. Data properties being preserved are the mean and the correlation matrix, meaning that each surrogate here will have the same mean, 0, and same correlation as the original data. So again, you would not define a metric to compare the two that is defined by the mean or the correlation matrix. So you could, for example, check the average one-lag autocorrelation across variables, for example. And here, well, let's have a first quick question where we want to know what we expect when we compare M0 and MS in the case of fMRI time series. So we compare average one-lag autocorrelation in original fMRI time series and in surrogate that are generated by this model. What do we expect? Do we expect that MO is equal to MS because autocorrelation is preserved by the model M? Do we expect that MO is different from MS because autocorrelation is not preserved by M and fMRI time series are autocorrelated? Or do we expect that MO is equal to MS because fMRI time series are not autocorrelated? So take a few seconds, try to make your opinion. Okay, so let's go step by step here. A first element is that we know that fMRI time series are autocorrelated, right? There is autocorrelation in fMRI time series. Second element is that this makes the assumption that each time point is generated by a Gaussian distribution, but independently from each other, right? So that destroys the autocorrelation structure of time series data. Hence, the correct answer here is that we expect MO to be different from MS because the autocorrelation is not preserved by M and fMRI series are autocorrelated. Okay, so conclusion here, if we find a difference, then that means that original data cannot be fully explained by a multivariate Gaussian, so by sigma. Again, this is the multivariate transposition, I would say, of the toy example I used with the distribution of heights. That doesn't mean that sigma is useless, right? Sigma is the correlation matrix, and we've seen in many applications that sigma is obviously very useful in these applications. Okay, so another illustration that rejecting the null is not that annoying in terms of usefulness of your metric. Now, let's move to the next level of complexity in terms of null models, where we consider first-order autoregressive representation. So that essentially assumes that each time point here is related to the previous one. So xt can be expressed as a function of xt minus 1 in a linear way through this matrix A that has the same size essentially as a correlation matrix and that relates all these time points. So essentially A is accounting for the first order autocorrelation structure of fMRI time series. From this, we can generate surrogate data. And here it's less obvious what data properties are preserved by this. And it is not complicated to show using these Euler-Walker equations that this null model preserves the mean, the covariance structure, and R1, where R1 is the first order autocorrelation structure. Okay, so if you have an autocorrelation between a region 10 and region 12 that is equal to 0.3 in the original data, you will have the same autocorrelation between these two regions in each of the surrogate samples here. So another way of framing that is that AR1, the AR1 null preserves first order linear and Gaussian properties in the data. So in this case, you couldn't use autocorrelation as a metric to distinguish between the two because it will be preserved by construction in the surrogate data. But you could, for example, check amplitude of sliding window correlation fluctuations, the curve that I showed in the first slides. or state structure, for example, so doing a sliding window correlation, clustering it into different states, and then checking transitions and things like that. Just mentioning here that that's a test that we did in this paper from 2017, and we show that it's actually not that easy to distinguish original from AR1 surrogates in this case. Okay, the conclusion in the context of fMRI is that this model, yeah, as I said, is harder to reject, which suggests that these time series are to a large extent well represented by linear and Gaussian models. That doesn't mean that the brain is linear and Gaussian, that just means that fMRI time series are, well, mostly linear, I would say, based on these metrics that we used here. And finally, I'm going to be maybe a bit quicker here, but I also wanted to mention phase randomization. That consists in taking the original data and randomizing the phases in the Fourier representation of the original data. And here, it's important to be aware of which underlying model we are actually testing for, because that allows to compare and to know whether we want to use a phase randomization versus AR1 versus multivariate Gaussian. And here, again, it's not very complex to show this, but it's not trivial either, to show that when we do phase randomization, essentially what we preserve is the complete autocorrelation structure. So we preserve the mean, the correlation, so static correlation, and all the autocorrelation structure from R1 to RT. Okay, so if we want to frame it in terms of null model M, that means that we assume that xt can be represented as a weighted sum of all the previous time points. And in this case, again, we can use the same metrics to compare between original and surrogate datasets. And in this case, that's also something that we showed in the paper, but that was shown also by others. It's also hard to reject metrics that are computed from original, in original and PR surrogate datasets. Okay, a little summary table here, where I have the three nulls that can be used in multivariate applications. In the case of fMRI, I would suggest to use the last two. The first one is very easily rejected because it destroys the autocorrelation structure. And well, if you compare a metric between the original one and multivariate Gaussian surrogates, well, it will almost always be rejected, but just because of the autocorrelation structure that is in fMRI time series. So it's not super informative. On the contrary, these last two are harder to reject, which suggests that if you account for the linear structure and even the first order autocorrelation structure of fMRI time series, you are actually capturing quite a lot of information in these fMRI time series. Okay, so you can see here that there is a nice nested structure. This one preserves sigma, this one preserves sigma and R1. So R1 is the first order autocorrelation matrix of fMRI of time series. It's the same size as sigma, except that it's non-symmetric. And here you preserve even more information, but it's a nested structure of preserved information. Okay. So it's quite dense. I realized that there is a lot of information, but I wanted, well, yeah, to sketch a bit the different models that are being used in the dynamic FC literature, and also to make the links between the two. But if you want more details, we can either talk more during the conference if you are lucky enough to be on site, or you can also go to the paper that explains these in more details with additional toy examples. Let's now move to the last part of the presentation where I discuss interpretation of the results. I've already alluded to that more or less using a few toy examples, but let's now be a bit even more concrete and think about this. So do my results need to be different on original and surrogate data in order to be relevant / interesting / meaningful? So again, I want to emphasize here that I've seen in quite a few papers that it has become a kind of necessary to compare a metric in original versus surrogate data and to show that it's different. Well, my opinion is that it's not necessary to find a difference between the two, but it can be useful to compare it to surrogate data. So I'm gonna explain this now in the next few slides. So let's represent the overall statistical information that is contained in fMRI time series by this disk, green circle. So this is all the information that you could get, that you have in fMRI time series. This is the statistical information that is captured by a multivariate Gaussian models. That means excluding autocorrelation information. If you then use the next model in terms of complexity, you could use the AR1 model, and then you will capture the covariance structure, but also the one lag autocorrelation structure. So you capture strictly more information from the original time series. Similarly, if you use PR, so that amounts to considering an ART model, so linear autoregressive representation of the time series, but with a horizon that goes much further in the past, then you capture even more statistical information. In light of this, let's now discuss the interpretation of a test result. So let's assume that the results are the same on original and AR1 surrogate data. Well, that just means that the method exploits information within the one preserved by the AR1 null. So, for example, let's be very concrete. Let's say that you compute brain states, you do a sliding window correlation, you have 5 clusters, and you find that the transitions between the clusters are the same in your original data and in the AR1 surrogate data. That just means that this clustering and the transition matrix is reproduced, is captured, is hidden within the AR1 information, meaning within the covariance structure plus R1 structure, okay? But that doesn't mean that this representation in terms of 5 states is significant or more useful for a clinical application or things like that. It's just a statistical description of the nature of this clustering into 5 states. Let's consider another case where the results are different on original and phase randomized surrogate data. So in that case, here is the second question: which curve could represent information that is used by the method in that case? So for example, again, you identify states using a sliding window correlation in original and in phase randomized surrogate data. You find that the transition between state 1 and 4 is different in original and phase randomized surrogate. Well, this means that you are exploiting, so this transition between state 1 and state 4, for example, is exploiting, at least to some extent, information that is beyond the information that is captured, that is preserved by the PR null, okay, this light blue curve. So it must be curve number 1, because 3 and 2 are all within the PR circle, which makes it impossible to distinguish between original and your surrogates, right? So you couldn't find a different results in original and surrogate in that case. Okay. Last few remarks and open questions. First, the fact that even if you are within the PR null, so finding that your whatever metric or representation of brain dynamics is preserved by the PR null, keep in mind that this corresponds to an autoregressive representation of order t, which means that it's described by t plus 1 times n squared parameters, where n is the number of brain regions and t is the number of time points. So this is huge in terms of parameter space. And so while it can be termed trivial, this null, because it's linear and Gaussian, it's not trivial in terms of parameter complexity. And then, and I think this is a very tricky and interesting and unresolved question, which proportion of statistical information is captured by these models? Because I've shown here the little sketch on the left, but it might be that actually the linear information is actually very small within all the information that we have. And well, this needs to be further tested. We think that we are closer to the left representation versus the right one, but it's unresolved and I think not easy to definitely answer. Here we are talking about statistical information, but we also are interested in meaningful neurological information. So it might be that, well, the most neurologically useful for clinical classification and things like that, for example, is in the dark blue area here or in the green area. So that's also an open question. I have no definite answer for that. It seems that the blue circles are doing quite well in terms of links to disease, to behavior and things like that, but it's also an open question. Let's now come back to the two applications that I mentioned earlier. The first one by Zaleski and collaborators, where they define the different states from a sliding window correlation approach. So in that case, the null that they use was a bivariate autoregressive representation. So that means that each pair of brain regions was considered separately. And so in that case, well, it's quite obvious that you will reject the null because we know that, well, several regions co-activate together. That's why we have resting state networks and things like that. And so by considering only bivariate AR, you destroy this structure. And this conclusion only means that the dynamics that are presented here cannot be represented by only bivariate interactions. You need to account for the whole multivariate structure of the data. Does this mean that these states do not exist or do not have neurological interpretation? No, these states do exist. The brain transitions between phases of high efficiency or connectivity and low connectivity. It's just not well represented by bivariate AR. And well, what we showed in our comparison between original and multivariate AR nulls is just that these states are well captured, are hidden within this AR1 representation of fMRI time series. Vidore and collaborators show that these states, brain states, are organized into two metastates. So how should we now interpret their results in light of what we've seen? Well, first, that the different nulls that were considered allow to make different conclusions in terms of the statistical nature of the original time series. Again, the bivariate null is easily rejected, but we've seen why. It's kind of obvious. And the multivariate AR is capturing quite well, actually, this distribution, this clustering into two metastates. And as said in the discussion of that paper by the authors very well, they say, importantly, although a subject-specific multivariate AR model contains the information that is relevant to the metastates, these are not straightforwardly revealed in the parameters of this model. In other words, it's fine that the MAR1 null reproduces this structure. The added value of this representation is not weaker, right? The added value is still there, and the description in terms of different states that cluster into two metastates is still completely valid. It's just that it is captured somehow in a complex way within the MAR1 model. So 3 final take-home messages. First, essentially, it is not mandatory to perform null model testing to validate usefulness of your metric of interests for fMRI dynamics. So it's not going to be informative about neuroscientific relevance for fingerprinting, classification, and things like that. So here I'm talking about comparing original and surrogate data, right? I'm not talking about relating a metric to behavioral information, for example. So just describing the nature of the metrics by comparing original to surrogate is not going to be informative about relevance of that metric. Then if you want to use a null, it can still be useful, but in order to understand the nature of the statistical information that you are exploiting. For example, again, if you have a classification into 5 states, you compare it in original versus PR surrogates, and you find that the transition matrix is to a large extent the same. Well, that means that these transitions between the states is essentially reflecting linear effects in your time series. But that doesn't make these transitions not significant or things like that. I have the impression that I'm repeating a bit myself, but I think it's really key and maybe sometimes misunderstood currently. A final word by Tom Nichols. So I had the opportunity to present this work to his group, and he summarized these findings like this. And he said, overall, this suggests we should shift our interpretation of these tests from significance testing to system identification. So this is out of memory. So I hope I'm faithful to what he was thinking, but I think that's what he meant. And I think that's a very nice way of seeing it. I didn't frame it myself in that way, but I think this can be also useful to, well, to reframe what I'm meaning here. So essentially saying that we do not do significant testing as we would do for example, checking whether a correlation is significantly different from 0 or not. Here, that's not what we are doing when we compare original fMRI time series to surrogate time series. We are rather checking what system, what model is a good representation of our original time series. And that's also very useful in order to define the most relevant metrics, for example, or the most efficient in terms of complexity. With this, I end with a few references. The main one is the first one, in which we detail the whole presentation here. I thank you for your attention. I now let you with the next talk. I think it will be by Joanna. And I will be happy and I hope to see you soon all in Glasgow. Have a nice end of the day.